Welcome to fourth lecture of Analog Microelectronic Circuits Unit 4. We were discussing operational amplifiers, and the last class we have uh, seen about instrumentation amplifier. So today we'll discuss one more linear op-amp circuit, which is precision rectifier. Precision rectifier. So we know that typical rectifier, as you have done the rectifier experiment in your AMC lab, for a typical rectifier, it will rectify voltages. It will rectify voltages which is greater than the cut-in voltage of the diode which is used. Generally, it will rectify voltages greater than 0.7 volts. That is what you have seen in the lab also. So for such rectifiers, if you look at the transfer carrier of such rectifiers, if I plot V in versus V out, so output will follow input, but it will happen only after that particular cut-in voltage. So your transfer carrier will be for positive V in. After 0.7, output will follow input. Similarly, for negative V in also, output will be positive, but it will follow after 0.7. So this is the typical rectifier transfer carrier. But now using op-amp, if we use op-amp, we can rectify using op-amp rectifiers. Using op-amp rectifiers, we can rectify voltages in the range of millivolt or microvolt. We can rectify even voltages of this range. So when we say we can rectify voltages as small as milli or microvolt, the transfer carrier will be like something close to this, because when your Vin is slightly positive, your output will be positive. When your Vin is slightly negative, output will be positive. So this is what we are expecting out of using an op-amp based rectifier. So to start with, what I'll be doing is I'll be taking an op-amp. So since it is a linear op-amp linear circuit, we'll be using op-amp in negative feedback. So using a regular diode, we can rectify voltages more than 0.7. So the idea here is to use that regular diode, but in the feedback path of an op-amp, in the negative feedback path of an op-amp. So use the same diode in the negative feedback path of an op-amp, and basically I'm getting output voltage from this point. I'm dropping a resistance RL over here to measure the output voltage, and the voltage to be rectified will be given to the non-inverting input terminal. So whenever we use a diode in the negative feedback loop of an op-amp, this combination is called as super diode. This combination is called as super diode. Why? Because this combination can rectify voltages. Even the slightest positive voltage it is able to rectify. So what we are expecting out of this is, let us see how what is the minimum voltage that this rectifier can, this super diode can rectify. So we know that for an op-amp, output can be expressed as V non-inverting minus V inverting into the open loop gain of the op-amp. So assuming open loop gain as infinity. So since the op-amp is in negative feedback mode, virtual ground property is valid. So I can write output voltage by A is equal to V non-inverting minus V inverting. Now so V non-inverting minus inverting, this is basically what is a V non-inverting voltage? V non-inverting voltage is your V in. So V non-inverting voltage is V in, right? Right, so V inverting voltage initially, see, so this is the inverting voltage. Assume that initially the drop across the resistance is 0. So I can write output voltage by A as V in, or now if this point is 0, and if say if this diode is on, output voltage will be 0.7 divided by let us say value of A as 10 to the power of 5, very large voltage. That means your Vin can be as small as 7 microvolt. Right. So what I have done is I have placed a diode in the negative feedback loop of an op amp, and the diode equation is valid there. My output is actually a finite value, so I can apply negative. I can actually apply virtual current property. Now, assuming initially if the output is 0, in that case I can write V naught by A as V in. That means V in can be as small as 7 microvolt, or for even that low voltage output will be able to you will get an output voltage which is a rectified output voltage. So that is a basic idea of a super diode. Right. Yeah. Now in this case, so let's assume your V in, if your V inverting voltage, the input voltage is greater than 0. So when that happens, when your input voltage is greater than 0, what I can expect here is actually a positive voltage that will make this diode turned on. That means you have a negative feedback loop. So that means if the negative feedback is established, your virtual current property is valid. So V inverting is equal to V non-inverting. So what is V non-inverting? V inverting is same as V non-inverting. That will be equal to V out, and that will be equal to V in. Right. So basically, when the diode turns on, your output will be same as input. So so in this case, this combination is basically working as a half-wave rectifier. Right? So when your input is positive, what I can expect here is a positive voltage that will make this diode forward biased. If the diode is forward biased, you have a negative feedback, unity gain negative feedback loop. So that is basically a voltage follower. So this voltage, that is a inverting voltage, will be same as non-inverting, or your output will be same as input. So in that case, I can draw the transfer kara of this circuit using the super diode. When your output is positive, when your input is positive, you will get a positive output voltage. So what happens when your input is negative? When your input is negative, your output, the voltage what I can expect is a negative voltage that will make this diode turn off. If the diode turns off, there is no feedback here, so I cannot expect the same voltage at the output. So basically your output will be 0. So for this circuit, when your V in is greater than 0, V out will be equal to V in, and when V in is less than 0, V out is equal to 0. Right. So the super diode in this combination will simply work as a half-wave rectifier. So the two things we need to understand here: op-amp based rectifiers, otherwise they are known as precision rectifiers because they can rectify voltages as small as milli or microvolt. So whenever a diode is used in a negative feedback path of an op-amp, and when the diode turns on, your output will be equal to input, and this will act as a proper half-wave rectifier. Right. Now moving on. So what we have seen here is if the input is positive, you will get a positive output. Now what about negative input voltages? So whenever you have negative voltages, how to get rectified? So for that we have another combination. What we can do is, again we'll take an op-amp and I'll be directly taking up the circuit. So this is a V in. So non-inverting terminal will be grounded. So I'll be using so I'll be using two diodes. So one diode in the feedback path and another diode at the output side. Now this circuit can actually give you a positive output when you have a negative input. So that is the whole idea. In the previous circuit we were able to get the other way. So I'll just number these diodes, say this is diode D1 and this is diode D2, and this is your output voltage Vout. So now for time being I'll assume that both resistors have the same value, R1 equal to R2 equal to the same R value. Okay, so now let's look at the working of the circuit. Say if your Vin is greater than 0, so when your input voltage, so the voltage here is a positive voltage, that positive voltage will definitely so let me number in this way. No, you can have either number. So this is D1 and D2. Now say your input voltage Vin is greater than 0. You have applied a positive voltage here. That positive voltage will definitely turn this diode turns on. So when you give a positive voltage to the inverting terminal, the output voltage what I can expect is actually negative voltage. So because of that negative voltage, this diode will be turned off. This will be on and this will be off. So when your Vin is greater than 0, diode D2 is on and diode D1 is off. Right, now now you have diode D2 on, that is actually making a closed path here. It is basically giving a negative feedback path is established, right? So say I'll mark this voltage as some V1 also. So D1 is off because V1 is negative. Okay, so you have this negative feedback loop established. That means your virtual ground property is valid, right? But what you can see here is diode D1 is off. Since your diode D1 is off, so if I draw the equivalent circuit, maybe that will be helpful. I'll draw the equivalent circuit here. So this is minus plus, this is ground, this is actually the input. Now diode D2 is on, so this is short, but this is off. Now you have a resistance R2 connected to this side. So this is Vin. Now this is since negative feedback is established, virtual ground property exists, this node is actually at 0 volt. So what will be your output voltage? Your output voltage will also be equal to 0. So in this case you will not get any output when your input is positive. Now for the same thing, what will happen when I apply a voltage which is less than 0? So when you apply a negative voltage here, this negative, that means here you are getting a negative voltage. That will make this diode D2 off. But because of negative, your V1 voltage will be positive. And that will make your this diode D1 on. So here D2 will be off and D1 is on because V1 is a positive voltage. So let me draw the equivalent circuit. When I draw the equivalent circuit, this is minus, plus, this is V in. Now you have D2 off, so that will be open, but your D1 is on. That will make your circuit something like this, right? This is, you have an open circuit here and you have a short circuit here. That is anyway it is done. So you have R1 and R2 of same value. That will simply work this as a inverting amplifier. Now when your Vin is negative, inverting amplifier will make your output positive. So your output voltage will be equal to Vin itself, right? So this is again what we have done here is we are using diode in the feedback path of an op-amp. So and this is working as a half-wave rectifier. So for Vin positive, your output is 0, but for your Vin negative, your output is actually equal to Vin itself. Sorry, minus of Vin. So I should write here as this is minus of Vin. This is not Vin because this is working as an inverting amplifier. Or you can write Vout is equal to minus R2 by R1 into V in. For same value resistors, you will get V out same as minus V in. So if your V in is negative, your output will be positive. So that is what happens in this. So this I can call as a half wave rectifier, precision half wave rectifier, which rectifies only for negative half cycles. The previous circuit was acting as a precision half wave rectifier, which rectifies for positive half cycles. Now with that, maybe we are interested in one more circuit where which works as a precision full wave rectifier. So there is another op-amp based circuit, precision full wave rectifier. Yeah. So here we'll use two stages of amplifiers. So being this is the point where we apply the input, and we need to use diodes in the feedback path. So this is the way which we connect. Now one more diode will be connected here, and that will be connected back to this point. So I'll mark this as R and R. This is diode D1 and this is diode D2. Right, so this is the first stage. Again from this stage we'll connect towards one more stage of op-amp. This is minus and plus. And this is your output voltage. So again these are connected using two resistors R and R. Yeah, you have one more resistance over here. Yeah, so this is the basic circuit for doing full wave rectification. So let me explain how this circuit works. So I'll mark this voltage as say some V1 voltage and this as some V2 voltage. Now yeah, so let me start by looking at two different cases. Say I'll take case 1 as when you apply input voltage which is positive, when your Vin is greater than 0. So let's see, when you apply a positive voltage here, when you apply a positive voltage or when you apply a voltage which is slightly greater than 0, yeah, so this node we have positive, but since it is given to the inverting input terminal of the op-amp, V1 voltage will be V1 voltage will be negative. Now if your V1 voltage is negative, most likely diode D1 will be on and diode D2 will be off. D2 is off. Right. So since we are giving a positive voltage here, what we can expect is diode V1 will be D1 will be on and D2 will be off. Now yeah, so you can see that since D1 is on, you have a negative feedback path established. So this voltage or virtual ground property exists. So this node will be same as this node. That will be equal to 0. So I can actually expect a 0 voltage here. Yeah. So yeah, so since virtual ground is established, yeah, this is 0. Now let me look at the voltages. So D1 is on. So you have this, the first op-amp is having a negative feedback established, and that will simply work as a inverting amplifier. So my V1 voltage will be equal to minus of Vin. V1 will be equal to minus of Vin. At the same time, I can say that V2 voltage will be equal to 0 because this diode is off. Basically this is off. D2 is off. Right. So or I will draw the equivalent circuit here for a better understanding. This is the first op-amp. This is resistance R and V in. Now this is another resistance R. This diode is on, so D1 is short. And you have another diode which is actually off, so that is off. Now what you have here is that is connected to that is off, right? So that portion is done. Or we have, yeah, basically yeah, that way. Now from here you have another resistance R. This is minus plus, and this is the resistance R here, and this is V out. So this is R, this is also R. So because of virtual ground property, this node is 0, so this is also at 0. So basically what I can say is there is a resistance connected from the non-inverting input terminal of this op-amp. Yeah, that is connected to 0. So I can assume that you have a 0 voltage coming at this node, right? So let me write this voltage as, so this is my V1 voltage, that is equal to minus Vin. Now that is going as the input to the second stage. So what you can see, second stage is again another inverting amplifier. So output voltage can be written as minus R by R into V in. V in is V1 here, so it is minus R by R into minus V in. So basically your V out will be equal to V in. Right, V out is equal to V in. So for this circuit, initially I assumed input voltage greater than 0. I have written the voltage V1 as negative. So with that, I can write the condition of D1 and D2. D1 is on and D2 is off. So that will give you the equivalent circuit of this. So D2 is open. So from because of virtual ground, this node is 0. The same 0 voltage I have considered at this point also. This is also at 0. So now with the equivalent circuit, when you give V in here, this will simply act as an inverting amplifier. So your V1 will be minus V. Again, one more inverting amplifier, your output will be inverted again. That means for positive half cycle, if you draw the transfer cara V in versus V out, for positive inputs, your output will be positive. That is basically because of two inverting action happening within the circuit. Right. Now, that is okay. That is fine. Now let us see what happens when for the same circuit, when your V in is, we'll consider case 2, when your V in is less than 0. So if I look at this circuit, when your V in is less than 0, when your V in is negative, what I can expect here is actually a positive voltage because of inverting action. So that will make your D1 off and D2 on. So with that, I'll draw the equivalent circuit and I'll proceed further. So with that, I'll write my V1 voltage as positive. If my V1 voltage is positive, D1 is off and D2 is on. So D1 is off and D2 is on. So with that, if I draw the equivalent circuit, this is minus plus, plus is grounded. You have one resistance over here R. Now feedback, you have another resistance. But now here this is the D1 position, but D1 is off, so that will remain open. But D2 is on, so that will make this connection. This will be the connection. So this is R. This will remain open. Now this is the V1 voltage. So this is V in. Now this is connected to the next resistance R. That will go to second op-amp, where you have a feedback resistance, and this is the final output of that op-amp, and this is connected to this point, which is basically our V2. Right. Now let me mark these things. This is the equivalent circuit now. Now let's see if Vin is less than 0. If your Vin is less than 0, yeah, so you can still see that you have a negative feedback here, because from the negative you have a connection back to the positive, back to the output terminal. So you have actually a negative feedback established. There is no positive feedback as such, but there is a negative feedback, but through the second op amp. So now because of that, I can say this these both points will be at zero voltage. Now say if a current flows here, that current will actually flow, one path will be this and the other path will be the down path. So let me write an equation there. Okay, one more thing. So this is V2. So I'll mark this as V2. Now because of negative feedback, this is also V2. So now if I write the current as V in by R, which is actually the input current, that current will split into two. So that can be written as 1 is actually 0. This node is 0 minus V2 divided by R, which I'll mark as some I1 current. So this is your I1 current, plus another current will be here 0, so that I'll mark as I2 current. So that is 0 minus, this node is V2, so 0 minus V2 divided by 2R, 0 minus V2 divided by 2R, which is your I2 current. So from this, if I write an expression for V2, so let me write in this way, V in by R is equal to minus V2 by R minus V2 by 2R. If I take these things, so I can write this as, this will give you V2 as minus 2 by 3 into V, because you can cancel the R terms. So this is a V2. Now this is the voltage actually coming here. So what is a V2 voltage? V2 voltage is minus 2 by 3 into V in. So that is coming to the minus 2 by 3 into V in, that is a V2 voltage, right? So now if I consider only the second op amp, because anyway I understood what is V2 voltage. So if I consider the second op amp, so this is minus plus, this is your V2 voltage. Now to the inverting terminal you have actually two resistors in series. I'll mark as 2R. The other point is connected to ground, so this I'll ground. We have another resistance R connected here, and this is output voltage V out. Now if I look only at the second op amp, this is actually acting as a non-inverting amplifier with output voltage 1 plus feedback resistance is R by input resistance is 2R into V2, or this is basically 3 by 2 into V2, where my V2 is minus 2 by 3 into V in. So this is my output voltage. That means your output voltage is equal to minus of V in. That means when your input voltage is negative, your output voltage is negative of input voltage. That means still your output voltage is positive. That means for case 1 we have seen, for a positive input your output is actually input voltage itself, and for negative input now your input is minus of V in. So this will be the transfer care of this precision Fullwave rectifier, which rectifies for both positive and negative voltages in the range of milli or microvolt, right? So this is all about precision rectifiers using op amps. So basically the idea is to use a diode in the negative feedback path of an op amp, and thereby making it as a super diode which can rectify voltages as small as possible. So this is super diode which works as a rectifier, half a rectifier. This is another one which works for the negative half cycle, and this is the circuit which works for both half cycles, right? So that's all about precision rectifiers. Now one more thing I want to discuss here is the Schmitt trigger discussion. We have done the discussion in class about Schmitt trigger. So I'll we have seen the open loop configurations where your output voltages will be switching between plus and minus VSAT voltages. So we have seen a particular configuration called Schmitt trigger, where we employed a positive feedback and thereby established the upper threshold and lower threshold point to get basically it acts as a squaring circuit. Now in that we did this problem having UTP and LTP of symmetrical voltages, one on plus side and one on minus side, and to get different voltages on plus and minus, we also discussed that we should actually put a diode. There is one more thing. If you want to have voltages both UTP and LTP as positive or both UTP and LTP as negative, one another circuit is actually to connect a reference voltage in this way. So the very basic circuit with the positive feedback, but the end of R2 is not connected to ground. We will be adding a reference voltage there, and the corresponding equations of UTP and LTP are this. Upper threshold point is Vref plus VCC, the voltage coming here, VCC minus Vref, this voltage, into R2 by R1 plus R2, and LTP voltage is this. So in order to solve this, so you should know these expressions for UTP and LTP. To solve this, let me consider these as X. For X, I can write this as UTP equals Vref plus VCC minus Vref into X, and LTP equals Vref plus minus VCC minus Vref into X. So now you can enter the values of UTP and LTP. So if you enter the value of UTP as 2 and LTP as 1, and if I subtract this, I'll get 1 is equal to Vref minus Vref will be cancelled. VCC is 15 minus Vref into X minus 15 minus Vref into X. So if I solve this, I'll get it as 15x plus 15x will be 30x minus Vref x and plus Vref x will be cancelled. So I'll get x as 1 by 30. So x is basically R2 by R1 plus R2, that is equal to 1 by 30. Take values of R1 as 1k and R2 as, in this way, so that you will get the two resistance values, and Vref can be calculated again by substituting back this ratio over here. You will get the Vref value. So Vref is 1.55. Right. So that I want to summarize here. For Schmitt trigger, say if you want UTP equal to plus A and LTP equal to minus A, same symmetrical voltages, you have to actually use this circuit where you will give input here. This is your V out and this is your V in. This is your R2 and R1. This is the circuit what we have discussed here. Right. Now, I'll use the same thing, R1 and R2. Now, if you want to have UTP of plus A and LTP of minus B, so what you need to do is minus plus can actually use two resistors, one with the diode in this direction and another with the diode in this direction, and connect to the output. So when your output is positive, it will take this path. When your output is negative, it will take the other path. So this you can call as R1 dash and R1 double dash, and this as R2. So this is case 1. This is case 2. So this is case 1 and this is case 2. Now case 3 is what we discussed just now. UTP equal to plus A and LTP equal to plus B, or the other way also. So minus plus, connect a reference voltage Vref, and this is your R2 and R1. This is V out. So there we have expressions for UTP and LTP. What we have written just now. These two expressions. With this we can design. So these three categories of Schmitt trigger is also important, so you can understand the UTP and LTP equations, and thereby you can design it, right? So that's so this Schmitt trigger is basically a positive feedback circuit. Yeah, so with this I am winding up this lecture. We'll continue in another lecture.